Alright, let's keep chugging along. Friction is a contact force. Friction is a contact force that acts parallel to the direction of motion. Parallel to the direction of motion. So what does that mean? So we've got our car here, it's screeching to a halt, and this arrow right here, this represents the force of friction of the street on the car, So you can see that right there where those tires are screeching across the street, that street is putting a force this way on that car. That street is slowing down that car. So what did we mean when we said parallel? Well, we know that the car, you can see from these little lines right here, the car was moving this way, and the force of friction is going in this direction. These two lines are parallel. Now, which is different than a normal force, right? It is possible for the force of friction to be going in the same direction as the object's motion, but it just so happens in this case it is going in the opposite direction from the object's motion. So remember though, forces always come in a pair. So that car is exerting a force on the street. So you can imagine that right here where these lines are on the street, if you probably put your hand down and felt that street, it would probably feel warm because the car exerted all this friction force on that street. Okay, let's continue. Air resistance. That's a contact force. It's a contact force, just like friction, that resists the motion of an object through the air. You can think of it like a parachute, or think about this biker guy down here. It always acts in the parallel direction from the motion, but this one is even more specific. It almost always acts in the opposite direction. So this guy almost always opposes the direction of motion. It usually slows down the object. It can be ignored below about running speed. If you were in a really precise lab, you wouldn't want to ignore it, but for our purposes, if we're thinking about an object that's going slower than running speed, we're going to ignore air resistance as being a very high magnitude force. So you can think about it's pretty important for this biker. He's going to feel the force of the air on the biker, and it's going to be pretty strong. But it's not really that important for this little snail right here. There might be just a teeny tiny bit of air resistance on the snail. So little that you could just ignore it. Okay, so an applied force. Now this one is the one that makes the most sense to everybody. An applied force, that's a contact force. We've so far just been messing with contact forces. That occurs when two objects push on each other. Anytime you push on something, we consider that an applied force. And it always points away from the point of contact between the objects. So a 8-ball and a cue ball click into each other, and that's the point of contact. Now, the cue ball is going to feel the force of the 8-ball, and the 8-ball is going to feel the force of the cue ball. So if I were to draw the arrows again, there's a leftward force vector, or a leftward arrow, and that's the force of the 8-ball on the cue ball. And there's also a force, the same force, because forces come in a pair, of force of the cue ball on the 8-ball. Pretty straightforward force the applied force is. I said that like Yoda, didn't mean to. Tension force. A contact force. Tension force is a contact force that occurs when two objects pull on each other. Think of a string or a rope or a chain. You can pull on an object and there's going to be a force transmitted through that chain or rope or string. And it always points towards the point of contact between the objects. It always points towards the point of contact. For example, we have this crane picking up this pipe, and if I was going to draw this is the arrow that represents the upward force of tension of the crane on the pipe. This downward arrow represents the force of tension of the pipe on the crane. So when we're thinking about a force of tension, this one makes sense. The crane is lifting up that pipe, so that pipe must feel an upward force coming from that crane. And because it's transmitted through a rope or a string, we call it tension. All right, gravitational force. Now, gravitational force, this is our first non-contact force. Non-contact force that attracts any objects. It's a non-contact force that attracts any objects that have mass. If you have mass, you exert a force of gravity and you experience a force of gravity. And it always pulls objects down in the downward direction. Downward. And it's very weak. Surprisingly, gravity is very weak. It's a very weak force. Now, that makes sense. If you're standing next to your friend, you have mass, your friend has mass, but you probably won't feel the force due to gravity that exists between you two. It does exist. You could measure it if you had really precise instruments, but it's a pretty weak force. You need a lot of mass. For example, you need like the mass of an Earth to really observe this force. For example, you throw a football in the air, that football is going to come back down towards Earth because that football experiences the force due to gravity of the Earth on the ball. We always ignore the force pair though, so never forget that there's a force of the ball on the Earth. So just as that football kind of feels that force of the Earth, if it could feel, it would feel that ball. And it would be the same exact amount of force. It's the same magnitude. All right, last page. Free body diagrams. It's a diagram that shows all of the forces on only one object at one specific time. So let's look at this plane. We're not thinking about force pairs now, the force of the plane on the air and the force of the air on the plane. Now we're just focusing on the forces on the plane. So we know that we have like a force here. We usually call this a lift force. This is the force of lift, and that's the air, force of lift of the air on the plane. And we have a downward force. What's pulling that plane down? You guessed it, force due to gravity of the Earth on the plane. Now we also have this forward force. This is we always call it, when we're talking about planes, this is just plane specific forces. This is the force, we call this often thrust. Let me zoom in again. Thrust. Force thrust. And that's caused by the plane pushing on air and the air pushing back on the plane because of the propellers or maybe the jet. So that's the force of thrust of the air on the plane. And then in the reverse direction, we have air resistance. So this is the force of air resistance, AR, of the air on the plane. So all of these are on this one object. We're always talking about the forces on the object. Let's do a simpler one. If we can look at this stapler. So in the upward direction, we have the normal force. Remember, that's that perpendicular force of surfaces pushing up on objects. That's the force normal of the desk on the stapler. In the downward direction, this is the force due to, downward direction, you guessed it, force due to gravity of the earth on the stapler. And so this is just how we do free body diagrams. It's easy peasy lemon squeezy. You just have to start drawing these arrows, vectors, and writing what those vectors or those force vectors represent. So we have an upward force. That's going to be that force normal of the street on the car. In the rightwards direction, we've got the force of friction of the street on the car. And in the downward direction, we've got, you guessed it, force of gravity of the earth on the car. So just remember, on car, on car, on car. You're always drawing the forces on that one object at any given time. All right, you guys, good job taking notes.